Yeah, what we noticed through some of the surveys is that people are sometimes lacking a bit of practical information on isolating EVs and characterizing them. So these are two new sessions that we initiated this year. So it's an honor to do this. When I'm isolating EVs, I often feel like these Buddhist monks that make intricate sand paintings. Isolating EVs takes at least a full day, and once you're done, then you add your EVs to a well, and then you hope some magic data will come out. That's also what these monks do when the painting is finished. They take a brush and wipe it all out, because nothing lasts forever. So why do we go through this tedious process of isolating EVs in the first place? I think the first two speakers have already elaborated on this, but there are both EVs and non-EVs in your sample, and generally the amount of EVs is very or almost too low to measure directly. So you need methods to increase the EV concentration, for example by precipitation, ultracentrifugation, ultrafiltration, and tangential flow, to be able to measure them. On the other hand, we also need methods to increase purity. For example, a density gradient and size exclusion were already introduced, as well as immunocapture. So here you increase the amount of EVs over non-EV particles, and in an ideal situation you would combine the two methods. For example, combining UC with a density gradient and combining TFF and SEC, and this will give you the best of both worlds. Why is this important? Well, impure EV isolations can give rise to artifactual results. For example, if there are still biologically active proteins in your EV sample, they may cause the proliferation of your cells or affect the cells in your assay. So you don't want that if you want to claim that it is the EVs that are doing the job. This was also briefly mentioned by Olivier this morning. If you're working with transfected cells or if you're transfecting EVs, your transfection complexes may co-isolate with your EVs. So in the end, maybe you're just looking at transfected cells. Similar thing goes for lipid dyes. These form micelles that may co-isolate with EVs and may stain your recipient cells. So if you have these complexes in your sample, maybe you're just staining the cells directly. There are also many ribonucleoprotein complexes floating around. They contain RNA and may influence your sequencing results, and there are many papers that are discussing this. So it's good to be aware of all of these components. Anne already alluded to this. There's a balance between EV yield and purity. So there are some very crude methods that give a good yield with low purity. Other methods give something in between. And the methods that give you the highest purity will give you the lowest number of EVs. And if we think about purity, an elegant way of defining this is the particle to protein ratio that was first defined by Jason Weber and Elliot Clayton in 2013. And if you're interested in this is fairly easy to measure and could be important to report as well in your papers. But of course, whatever experiment you do, you're always limited by the amount of sample that you can obtain. And yeah, you can use whatever method you like, but it's important to be aware of the limitations of your method and adjust your conclusions accordingly. So today I will briefly discuss the commonly used EV isolation procedures, and I will highlight useful papers to get you started if you're new to the field. I will share some really practical tips indicated with the pipe tip, And I would like to convince you today that isolating pure EVs does not have to be difficult or expensive, and basically everyone can do it. So now it's time to get practical. A typical EV isolation protocol based on differential centrifugation would look like this. You first spin out the larger stuff at low speed, then take the supernatant and subject this to ultracentrifugation. After that you can run a density gradient, and then you can pellet the EVs from the floating EV fractions with another ultracentrifuge run. And the question that I often get is, how do you remove your supernatant after ultracentrifugation? And how I was taught to do this, it's documented in the paper shown over there. Just take a vacuum or a glass Pasteur pipette, connect it to a vacuum, start sucking off the supernatant from the top while rotating the tube until all of the supernatant is left. And then you can dry off the walls of the pipette tube, of the ultracentrifuge tube with a paper towel if you want to resuspend in a very small volume. Another thing, if you want to compare different conditions with each other, it's important to resuspend your pellet in a reproducible way. So by defining a minimum amount of pipette strokes, say 10 times up and down, you are much more comparable than if you just don't count. Here's a budget tip. Did you know that you can reuse your ultracentrifuge tubes? You can wash these with soap, and then by a thorough washing with hot water and demi water, and even autoclaving them afterwards, you can recycle your tubes up to 5 times. And I've done this all the way through my PhD working on RNA. Never had any problems. So this could be useful. Then the next step would be density gradient centrifugation. And I would recommend doing a bottom-up centrifugation that will float your intact EVs upwards because of the buoyant density. Because the risk is, if you load your sample on the top of the gradient, they may fractionate with non-EV particles or other things. So how do you do this manually in a handy way? I would suspend exact amounts of the density fractions, say 700 microliters with a P1000 pipette, and then use a plastic Pasteur pipette to take this liquid and put it on top of the gradient, because this gives you better control of the liquid flow. You can also do this automatically. So this is a paper from Anne Hendricks' lab, and what you can see on the images is that if you have a robot assisted system, you will get cleaner, sharper layers and more consistent results. Another tip I have is it's important to measure the refractive index of your collected fractions to be able to compare between gradients. Then if you want to get the EVs from the density solutions, you can out-dilute the fractions in PBS. You can even add some BSA to reduce sticking. And here it's important to notice that if you work with OptiPrep, you need to out-dilute your sample considerably, because OptiPrep, even at low concentrations, will form a gradient on itself. So it will be difficult to pellet all the EVs in this step. As an alternative, if you're only looking at EV markers on Western blot, you can also do TCA precipitation just to get the proteins out. Now, a more commonly used EV isolation protocol, or this is increasingly common, is combining tangential flow with ultrafiltration and size exclusion. So I will cover that now. So for the people who don't know tangential flow filtration, this is a concentration method based on a cross-flow membrane, as you can see in figure A on the right. And this crossflow prevents the blocking of your filter membrane by proteins as opposed to dead-end filtration. And this recent paper by Vizan and al. Reports that you get higher EV yields with TFF-based methods compared to ultracentrifugation. So this could be interesting if you want to isolate as many EVs as possible. After that, you will get about 10 to 30 mLs of concentrated EV sub. Before you load it on size exclusion, you probably want to concentrate it further, and for this you can use ultrafiltration. Here it's important to notice that the pore size of your filter and also the filter material will affect the recovery of your EVs. So regenerated cellulose is performing a bit better than polyether sulfone. But even within the group of regenerated cellulose filters, there is even a difference between 10 kD and 100 kD filters in terms of recovery. So it's important to be aware of losses in this step. To prevent losses even further, you can flush your filter material with PBS to recover more EVs. Of course, this will dilute your sample a little bit, but it's something you can do, and you can also do this with the TFF cassettes. Then about size exclusion chromatography. So this method separates large EVs from small proteins and lipoprotein particles. As the previous speakers already noticed, this is commonly used for biofluids as well, but works as well for cell culture derived EVs. And these don't have to be expensive. You can make them at home following the paper of Rink Nieuwland. So by putting resin in a syringe, you can make these columns yourself, and you can see on the bottom that it separates your EVs from proteins. Another thing, you can buy these commercially. These also give a good separation between EVs and proteins. And there are also automated systems, for example, the ECTA. And the nice thing about this is that there's an inline UV sensor that measures the amount of proteins that are eluding from your columns. So you get an online measurement of EVs and proteins that are coming off. Makes it easier to estimate where your EVs are. Whatever method you choose, EV purification may affect the composition and the functional effects of your EVs, as shown in this paper from Joel Nordin. So on the left you can see there are quite some differences in protein composition, and this also affected the biodistribution of the EVs. And the functional effects may also differ, as shown by this elegant study. So here they measured the effect of cardiomyocyte progenitor cell EVs on activation of HMAC endothelial cells. And here the SEC purified EVs were more potent than the UC derived EVs. So this is important to keep in mind. So when you've gone through this entire process of EV isolation, how do you store your precious EVs? So this is the recent paper by Andre Gergens in Jeff showing that EV concentration drops considerably during storage at -20 and even -80 degrees. And in this paper he compared various storage buffers on particle concentration and many other parameters. And he described a buffer named PBS hat that prevented EV losses. So this is PBS with HEPAS, albumin and trehalose. You can make this as a 10 times concentrated buffer in which you add to your EVs after isolation. So I would definitely recommend reading this paper. Because what's the problem? EVs are sticky. If you dilute your EVs in PBS, like he did in his study, 1 in 200,000, and then measure the particle concentration over time. Within the course of minutes, you see a decrease in the amount of circulating particles. So addition of BSA can reduce the loss of EVs. And in this paper from Van der Vlist in Nature Protocols, they recommend to deplete EVs from your BSA solutions by making a stock and ultracentrifuging it. So I would recommend that. You can even add BSA to your SEC wash buffers, as described by Zhang and all. Of course, this is not really compatible with proteomics approaches, but it does lead to higher EV yields. There are also a couple of low binding tubes on the market that may reduce EV loss during storage, but this paper from Simon van der Wakker shows that there are not really big differences based on what type of tube you use, at least in this short-term storage. Also in the paper of André Gurgens, there's attention paid to this, and what he shows here is that in PBS you get really big losses of EVs, but using the PBS hat buffer, this is largely prevented. So I think using special tubes doesn't improve storage stability that much. It's more important to use the right buffer. So now for the take-home messages, I think I've shown you that the choice of EV isolation protocol influences the EV yields, the amount of co-isolates, and the functionality. I think it's very important to test your protocols before you run an important experiment with precious clinical samples. Just make sure everything's working as it should. And I would recommend to stay in control of your purification. So throughout the purification process, just do quality control of your EVs, looking at protein markers, particle size, and all other parameters that could be important to you. And of course, it's important to report all your parameters, be transparent in your reporting using the EV track and MySEF guidelines, and to be aware of the limitations of your methods and adjust your conclusions accordingly. So I would like to thank all the mentors that helped me throughout the years, Esther Nolte and Marka Waube, Kenneth Witwer, and my current PI, Pieter Vader. And thanks to Edwin van der Pol for commenting on my slides. Thank you for your attention.